Hello and good morning. My name's Sam and I'm going to be doing another Leetcode question today in the style of a mock interview. The idea here is that we're using a Google Doc, even though it's much more painful than using an IDE because it matches more some of the tech companies, their interview process. So if you're interested in following along, I'm going to choose one at random. We'll do it from the algorithms, easy, and one I haven't done before. And I'm going to start a timer as well once we start this. And if you're interested in trying the problem yourself, there'll be a link in the description, as well as I'll split up the video into different parts so you can kind of jump around if you need to. So let's see what we get and start this interview. All right, so we're getting some sort of grid-based problem, it looks like. You're given a row by column grid, and this is number 463, island perimeter. You're given a row by column grid representing a map where the grid at that indice is equal to 1 if it's land and 0 if it's water. So grid cells are connected horizontally or vertically, but not diagonally. This is kind of like Conway's game of life. The grid is completely surrounded by water, and there's exactly one island, one or more connected land cells. So we're guaranteed that there's only one island. The island doesn't have lakes, meaning the water... sorry about that. The island doesn't have lakes, meaning the water inside isn't connected to the water around the island. Okay, so it's not a closed... The island can't have like a water cell surrounded. One cell is a square with side length 1. The grid is rectangular. Width and height don't exceed 100. Determine the perimeter of the island. Oh, that's kind of an interesting question. So we know that the grid can't be too big. We know that there won't be any cycles within the island. So basically, once you find an edge of the island, you can follow it around the whole thing and you don't have to worry about there being an inside. So I'm just going to do zeros and ones. So if this was the island, actually, let's do it with a table just because it'll look a little nicer. So let's just create a 4x4 kind of like here, and we'll shrink it down. I guess this is one of the advantages of having a Google Doc for once. So we can't have an island that shows something kind of like this, where, and the color looks like it's brownish. Can you do this? Yeah. So we couldn't do something like, this where there's a water in the center. So let's just change the color of this one to blue. Sorry. This is not actually relevant to the interview, but it is kind of fun to do regardless. So here we are. Okay. And was that worth a couple minutes? Who knows? But this is not allowed. No lakes inside. The centerpiece. So we're always guaranteed that there will be water on the outside connecting, and the island will be that there's only one island. So we can't have, like, say the case is here, something like this, where there's two islands. We can't have that either. Okay, so that's good. Good to know. The grid is rectangular, width and height don't exceed 100, finding the perimeter of the island. So what I'm hearing here is I basically want to know what I want to find one of the edges of the island. It doesn't matter where, so we could just iterate through this array until we hit a 1 instead of a 0, for example. And sorry, let's get this back to normal. There we go. And then once we have that, we want to calculate the perimeter by... So there's a few ways we could do this. One idea I had, was find an edge follow it all the way around because we're guaranteed to have a continuous sequence. I'm not sure exactly how to calculate that just yet. Another option is to have a set of rules where for every cell we check what its neighbors are, and if its neighbors is 0, we know that it has one edge. So here, for example, we're gonna here, for example, we know that it has a 0 on 2 sides, so it has 2 edges, whereas here it has only 1 edge because it has a 0 on 1 side only. Whereas here, again, we have 2 edges, so we can always count the edges for every cell. For every island 1 cell, count neighbors that are water 0. The sum of all of these is the number of edges, i.e. perimeter, because we're assuming that the cell sides are all equal to 1. And yeah, so let me just let's make sure this makes sense, makes sense and is a reasonable approach, because I can imagine how we would implement this one already. The first one I think would be a little bit more complicated. It might be faster because once you have a edge, you only have to follow around. So let's say this was an extremely large grid and the island's extremely small. You don't have to check over the whole array to find the island. But you can also apply that for approach 2. Once you find an island cell, you only search for island cells nearby rather than the whole grid. So there's kind of like 2 parts to this approach. So there's kind of approaches for finding island. One is to check every cell, track which is 1. This will be O of n squared for n sides. And then 2 is check till find island, track, then grow from there since connected. And it is actually still, it's O of n to find it. Well, it's O of n squared in the worst case. Let's say the island is in the small corner. But once you find it, it's just O of k for k size of island in cells counts. So technically the time complexity is the same for the second approach than the first, even though in practice it'll end up being smaller if the island is much, which matters if k is much less than n squared. So like the size of the island much smaller than size of grid, basically is what it's saying. We won't probably do this just yet because that's growing out an island is a relatively big problem of its own. Not that big, but we should keep it in mind. So I think what I'm seeing here is, so finding an edge following it all the way around will be kind of a O of k type problem. Whereas for every island cell, we have this O of n-ish, n squared-ish, O of n plus k, sorry. We could basically do approach 2 after using approach 2 of this one. Let's say this is A. So let's say we used approach 2A to find the island and then grow it, and then approach 2 here for every island cell, count the neighbors that are in water. So I think actually this is not exactly correct because these are sub approaches. So I think we want to first find the island and then grow it out. Before we get too far, let's think about the question a little bit more and let's look at an example. So we have a grid here, sorry, this is a 2D, a list of ints. We're not using NumPy arrays just yet. Question for the interview is whether you can. And it shows this image right there. And here the perimeter is those 16 strips. So let's have a look. When you have, if you're on, one of the things to note is if your edge is to the grid counts as water. because this one right here has 3 edges, even though it technically only has 2 water cells next to it. So 3 there, 3 for this one, 3 for this one, 0 for this one, 2 for this one, 2 for this one, 3 for this one. You add them all up, you get the correct perimeter. So I think this second approach right here is the one we'll want to do, because these both can be equivalent in time complexity once you know what cells are the island cells. And in fact, we can do this instead of having to grow it out. We can iterate through grid and store. So kind of the question here is, how much memory do we want to use, and store island cells in a dict. So here, O of k space for k island cells, O of n time to find island cells. So actually, I kind of like this a lot. If we're allowed to use this much space, then we are going to be golden. This is a question kind of for the interviewer. Whereas I think for this one, technically, if you grow out from the island, you're only using I need to decide on what n means. N is n sides, so it'll still be n squared time to find the island cells, because you have to iterate through all the cells. But that is the minimum amount of time you could spend. So this is optimal min time. And the reason for that is you have to check all the cells to find the island / perimeter, no matter what you do. There's no approach that can't check all the cells. And so n squared sounds bad here because it sounds like it's growing at exponential, but n is the number of sides. If we were to instead say number of cells, we could call that c. We could just say this is O of c, for example. These are equivalent. You just have to know what you're talking about when you refer to n squared. So we're comfortable with this one, I think. This one seems pretty good. This one also has O of n squared search to find all the island cells, but instead of storing it in a dictionary, we use a queue or stack. Let's say a queue, or let's say a stack of found cell, add neighbors that are islands, then keep popping, pulling from stack to finish to search through whole island. That's essentially the whole process. And the nice thing about that one is that's O of, I guess in the worst case, it's 4 neighbors growing out. I'm trying to think of a case where, let's say you start with this one, you add this neighbor, you pop this one, so now you have only one neighbor, one cell in the stack. You add these 3 neighbors, and you pop this one, so you have 3 in the stack. You pop this one, you add this one, so you have 3 in the stack again. I guess there's probably a type of, it's probably O of 1 on average, but in worst case, you might have imagine a single center cell that has neighbors growing out in every single direction in a fractal pattern. It approaches O of k, I think, for the number of cells. So technically it could be close to the second one here in terms of space and time. So it's important to look at all these approaches. I've spent 13, 14 minutes kind of talking about how we try to find an island. We have our pros and cons on our big O for these ones. And this one, the 1A, has kind of the same problem. Oh, I'm being quite silly, aren't I? Why do we even need to store the space at all? If we're searching through to find island cells, we don't care about the connections or whatsoever. Iterate through grid. Don't store island. Just sum up perimeter. All right. Took me a while to get there. You guys are probably banging your heads at the wall for that one. My apologies. as you go. So you don't even need a dict. You just search O of n squared or C time to find island cells, and O of 1 space to sum up perimeter as you go. So that's all we need to do. I think that's pretty straightforward, and I think I'd ask the interviewer, here's what I'm thinking. They'll probably say like, that sounds good, so let's do the implementation. All right, so what I'd like to do is iterate through the grid. So let's start with our skeleton. We're calling this find perimeter of our input array, which I guess we call grid, and it's a list of ints, and we're returning an integer output. A question we might have is whether the perimeter size could ever be larger than the overflow, the max int size. And the answer is probably no in this case, especially for a grid size of 100 by 100. We're guaranteed a valid grid. There's only one island in this grid, so we don't need to worry about multiple islands or internal loops, anything like that. Not that it would matter, I guess, for this approach right here. It would calculate the perimeter for all the islands altogether. And here is where maybe the growing out approach would actually have a value for if we extended the problem to deal with multiple islands, for example. That's something we can talk about in the second, once we finish this, assuming we do. So let's see, find perimeter. We're gonna create a perimeter variable that'll hold the sum of all the edges. And then we're gonna iterate through for cell in, let's see, for I in range length of grid, and for j in range, well, let's actually first, we're guaranteed that the row and grid size is the same. So let's just get the grid size as equal to the length of the grid. Let's just use that directly. And if this wasn't guaranteed, we'd have to do like some sort of if length of grid is equal to grid of 0, length of grid 0, something along those lines, and then return or raise exception. If not, something along those lines might exist, especially if there's nuns and stuff like that. So important to point it out to the interviewer. They might say, let's not worry about that right now. So I'll keep that outside. Oop. All right. So for every cell in the grid, if grid of ij is equal to 1, you could technically do it this way because a 0 would not check, but it's a good practice, I think, to be very clear in the if statement about what you're looking for. Okay, because what happens if we start to add more values that could also result in true? So is island. So now what we can do here is let's create a separate function. We'll call it count neighbors, and we'll be given the grid, which is the same, and we'll also be given an index I and an index j, and it'll return a count of all the values, counts neighbors including edges. And what I like to do with this one is perimeter plus count neighbors. And so the reason I'm pushing it over to a separate function is because you see how we're already kind of getting a pretty deep loop right here. We can clean that up a little bit just with some optimization. So let me show you what I mean by that. So we have this loop. Let me just finish this off. We've summed up the perimeter for every neighbor, and then we just return the perimeter at the end. So that's kind of the main concept, the main logic for this function. Let's see if we can slightly clean up the number of indents. So what we can do here is have a loop within, and just it basically becomes an inline loop. And this is a little bit shorter. We no longer have 3 levels deep. So for every row, we're checking for every column whether the number of neighbors, if it's if the grid is a island. Otherwise, if the grid is an island. Otherwise, we do nothing there. I think that's right. We don't need put an else in there. All right, and then finally we return n perimeter at the end. So both of these should be equivalent. It's good to write this out so that it's clear to the interviewer as well as you what your logic is supposed to be. And let's go back to this count neighbors. So there's 4 neighbors. And we could either do some sort of grid-based approach. I think it might be okay since there's just 4 of them. We could do it iterative, just directly by hand. So if if I minus 1 is less than 0, we could even just say if I equals 0, left neighbor is water. Elif, so let's do the left neighbor first. So the left neighbor is water if edge or 0. So if I is equal to 0 or the grid of I minus 1 j is equal to 0. So that's the left neighbor. Similarly, we can do that for the other ones too. So let's start copying it over. Let's do right neighbor first. So right neighbor is water if edge or 0. And so if I is equal to the length of grid minus 1, or yeah, length of grid minus 1, or I plus 1 is j, then is equal to 0. So if we're either at the edge or the value is equal to 0, then we add water over there, and that becomes a perimeter. Count water edges is a better way of putting it, because not neighbors. Neighbors could be misinterpreted as the island neighbors. Okay, so that's these two, and now let's do the vertical. So we'll do top. So we do j is equal to 0, and I stays the same, and j minus 1, count plus 1, and let's do bottom the same way, and bottom is water if edge is 0. And here if j is equal to the length of grid minus 1, because the length of grid, let's say the grid has 4 cells, the length of grid will be 4, but the last index is actually 3. And so when we do 3 plus 1, we would go over the edge, and that's why we're checking for whether j is equal to the length of grid minus 1. All right, and then we just return the count at the end. So we could optimize this, make it like some sort of loop or something. Let's say they wanted to count all the edges, including like diagonal corners. It would be worth starting to think about like some sort of like array and loop process. But when it's just 4, this is pretty straightforward and clear and should be just fine. All right, so we've got that function, we've got this perimeter. Let's see if we can spot any issues with it. So we know there's only one grid. We know 1 means a island. We know the size of this grid will always be between 1 and 100, because the question is, what if the grid's empty? What happens here? And a 0, it iterates over nothing, perimeter is returned as 0. That may or may not be what the interviewer wants. Maybe they want you to raise an exception. What happens if the grid row or columns are different? Things start to fall apart because we're using the same n. But that's where we would have a check if that was something we need to worry about. Okay, seems fine. I think we should have a go at it. We're about 23 and a half minutes in. So we've got our find perimeter. I'm going to do this one right here. And our grid is the same list of ints and int output. And then we just iterate like this. And it's not, you know, this is, while it's clever, it's not the easiest to read, I will admit. So what if we just put the original one back in right here? And let's just do that. There. I think that's a little bit cleaner and easier to understand, even if it's more lines of code. So we're going to keep that. So for every cell in the grid, if the grid is that cell is an island, the perimeter count the water edges for that island. And it could be 0 because it's surrounded by other island pieces, and that's totally fine. So this becomes O of n squared, n edges, or n sides, or O of c for cells in grid, depending on how we define this. Counting the water edges is going to be O of 1, because there's a fixed number of edges, and let's pull that in actually. And we can put it below. And we're going to have to do, unfortunately, a little bit of a, like this, and then self dot. And I think that's all we need to do. No tabs anywhere. So count water edges goes through all 4 neighbors as defined by the original function. Can you guys see this? Yeah. And increments the count if it's a water edge. Okay. Perimeter. So I think this makes sense. I think this should be all right. Let's find out. Oh, this indices must be integers or slices, not a tuple. Oh, sorry. This is where my NumPy formatting comes in. This comma actually should be close bracket, open bracket, like that, similar to this one. Because what I was thinking about is in NumPy, when you have a 2D array, you can do things like I, comma j to get the row column in NumPy. But with a list of lists, you have to do array of I, j. And this may be completely obvious to you. I just missed it. That's okay. I think that's fine, and that is something an interviewer will point out if it's relevant. Might not even be, because you usually don't run code during an interview. All right, let's see if it gets the correct answers. So for these test cases, it appears to work just fine. So interesting. This grid is not square. So was my assumption of a square grid wrong? Weird. Why would they test with a unsquare grid? Row is equal to grid length, column is equal to grid I of length. The grid is rectangular. All right, you know what? It's good. It's lucky we passed these test cases, but it would have failed on the actual submission. The grid is rectangular. The width and height don't exceed 100. So we're not guaranteed that the width and height are the same. So let's actually get the width and height. So let's call this rows is the length of grid, columns equal to the length of grid of 0. And we are iterating over rows and columns. And technically, that's all we need there. Once again, we need to check for the length of the grid. For the left and right neighbors, we're checking the length of the grid at that index. And the first one, vertically, no, well, here we're going to have to do this. And I'm going to have to rewrite all of this inside there, unfortunately, too, but that's okay. Okay, so J gets to use the second indice, so actually it should be like that. And the first one here uses the I is the rows, and this is the columns. So make sure the lengths are correct there. Similarly, we have to do it in here as well. So we've got our rows, columns equals length of grid 0. These are not the same. And when we do a check here, we're checking the I is going to be for rows. That's fine. And then J is for the columns. So there we are. Okay. So this now handles rectangular grids. Are there any other things we need to worry about with the rectangular grid? Anything special at the corners? Should be okay. We are doing our check for the edges there. So yeah, let's do a submit and see if the rows and columns works just fine. Yeah, so still the test cases are good. And let's do a submit now. This is where you have to always check your assumptions. I just assumed that the grid size was row or column. And good to see our solution was accepted. Very happy to see that. Interesting to see where it's faster and slower. I think we're finally getting to a point where the speed of the algorithm might be relevant to the speed, the actual runtime. You can see some people have slightly slower approaches, some have faster. So for example, here we're passing a grid for every count water edges. Even though it's technically like a pointer, there is some very minor slowdowns for Python interpreters. I think there are ways we could do this faster, perhaps inlining this within here. For example, counting the number of neighbors as you go is another option somehow. I'm not going to worry about these optimizations because at the core of the problem is what you're trying to talk to the interviewer. Actually, let me reword this. You can worry about these optimizations if the interviewer wants you to try to optimize them. So I kind of talked through with the interviewer about this question at this point. I'm very happy with the solution. Nice to see. We can kind of start talking about some extensions. We can talk about changes. So like maybe the interviewer asks like, what are some optimizations you could make here? Here's where I start to think about whether there's anything we could do for counting the number of neighbors a little bit faster. There is maybe an argument, that as you're iterating through, the neighbor on this edge, let's say you go from this cell over here to this cell, you know that this edge has gone from being your right neighbor to your left neighbor. And in fact, you also know which neighbors to go to if you're in a water cell. So if you're in a water cell, you can skip all the neighbors that are water also. You could also, let's see. Once you found your island cell, you could just search for neighbors. You can search for other islands nearby instead of just iterating through the whole grid. And so what happens there is you would get something that might be a little bit faster instead of a guaranteed. So let's go back to this one right here. This was approach 3B. Let's call it approach 3C. So iterate till find island, then grow island. So the idea there is this original approach will always be n squared c, always looks at every cell, which technically is not necessary. You could, the idea is island is connected. Don't have to look at every cell once you find an island. In a perfect world, if you knew where one island cell was, you could start and grow from there. I'm starting to think about something else that's kind of interesting also, which is you can kind of use the row and column to think of it as island segments rather than island cells. So here the second row has 3 island cells in a row. You know, based on the number of island cells there are in a row, that there is exactly 2 edges no matter what, because it's a connected island. Well, no, that's not true, because you could have like a C shape or a U shape. So actually I take that back. You can't do that. But this you can do. If you knew where the island was, you could start and grow from there. Would be O of K for K island cells, where if K is much less than C, this is better. But in reality, if you don't know where the island is, you have to find the island and grow it out. So let's just say if K is much less than C, you do O of C search, which averages to, let's say, O of C over 2 to find an island. And then you do a K grow along there to find all of the island. So one could say, not in big O, because in big O you're still doing C plus K, which is the same as the previous one. You know, this is the same thing, but in practice, I don't remember what the notation is, like either I or something like that. It becomes C over 2 plus K, and C over 2 plus K might be a lot less than C plus K, or just C, you know, for the approach B. So that's the question. If C is a lot bigger than K, you could save quite a bit of time by just doing half, on average, half the island, half the grid search plus the size of the island. These are things to talk about with the interviewer. You can kind of suggest different things there. There are some changes, like here we've done something that has a, this has become a O of n squared equals O of c time and O of 1 space, because we're not actually storing anything here. Technically, when you're passing in the grid, you might be storing a little bit. It might just be a pointer, depends on the implementation. But this could become a pointer, so it'll still be O of 1. You can't, in big O world, in big O space, you can't do better than this, because in the worst case, the island's a single cell at the very end of the grid, and you don't know where to search in the grid, so you have to look through all the cells to find it. Okay, feel pretty good about that. I hope you guys enjoyed that, and if you followed along, I'll be interested to see what you found quicker, slower. Let me know what you're thinking. If there were any optimizations, I'd definitely love to know, but hope this helps, and see you guys next time.